In section 2.1, we talked about cut edges or bridges, and those were single edges that you could delete in a graph that would disconnect a connected graph. And in section 2.2, we talk about an analogous result or analogous definition for vertices that you could delete to disconnect a graph. So if G is a connected graph, we say that a vertex V is called a cut vertex if G minus V is disconnected. In other words, if you take out V, which also includes taking out any edges that are incident to V, then you're left with a disconnected graph. And just like with the bridges, we have an analogous definition for if your graph is already disconnected. So if G is a disconnected graph, we would call V a cut vertex if removing that vertex V would disconnect the component that that vertex is on. So in the following graphs, it's worth taking a minute to look at them and try to think through and see, do any of these graphs have cut vertices? In other words, is it possible to delete a single vertex in any of these graphs so that the resulting graph is disconnected? So you might want to pause it and think about it for a second. So let's look at graph G. Are there any cut vertices here? Well, you can start trying to think through it. If I deleted C, I would only delete C and then this one edge, so the resulting graph, of course, is connected. Similarly, if we deleted E, you would be left with, right, take away those two edges as well, and you're left with this path. So there's actually only one cut vertex in this graph, which happens to be the vertex B. And if you're not sure why that is, then just delete B and all of the edges coming out of B and see what's left. If we deleted B, we would be left with this graph. Right, this little path here from A to D to E, and then the individual vertex C. This has two components, right? Here's your first component and your second components. So G minus B is disconnected, which means B is a cut vertex. Now H actually has two separate cut vertices. If we were to delete the vertex G, the resulting vertex would look like, the resulting graph would look like F on its own, N on its own, and then this sort of little claw section over here with I, J, K, and L. This is definitely disconnected. It has three different components, the single vertex F, the single vertex N, and then this little claw part. So this is disconnected, which means G is a cut vertex, but using that same idea, I is also a cut vertex if we were to delete it. So just to be clear, this is G minus little g. Oh, wait, hang on. Name of the graph is H. H minus little g. If we were to delete the vertex I, we would be left with this sort of line segment here, F to G to N, and then these three single vertices over here, just J, just K, and just L. So this has four components, right? Here's one component, 2, 3, and 4. So this is disconnected as well, which means both G and I are cut vertices. And you can go through and convince yourself that none of the other vertices here are cut vertices. But G and I are both cut vertices of H. Now down here in graphs capital I and capital J, we actually don't have any cut vertices. And you should convince yourself by trying to either visualize what these look like if you were to delete any single vertex, or actually draw out the graph if you delete any single vertex. But deleting one single vertex is not gonna disconnect I. And similarly, J is already disconnected, but you're not gonna be able to disconnect either one of these components by deleting a single vertex, right? If you deleted just R, you'd be left with a path. If you deleted any one of these single vertices, you'd be left with a path, and similarly over here. So there's no cut vertices in examples I and J. Now, a good question to think about would be, is it possible for a graph to have a cut vertex but no bridge? And is it possible for a graph to have a bridge but no cut vertex? Right, so if you look at these examples up here, in these first two graphs, G and H, they both have bridges. Remember, a bridge or an edge would be a bridge if and only if it's not part of any cycle. So this would be a bridge of the original graph, and every single edge here is a bridge in the original graph H. But in these two examples, I and J, there were no cut vertices, and there were also no bridges because every edge is part of a cycle. And so it seems to suggest, just looking at these exercises, that maybe every graph with a cut vertex also has a bridge, or vice versa. So again, I don't want to give away too much here, but you should think about whether or not this is possible. And one thing to remember here is if you wanted to try to construct a graph that had a cut vertex but had no bridge, such a graph would have to have the property that every edge is part of a cycle, but there is some vertex you could delete to disconnect the graph. Okay, so I'll let you try to think about that and come up with an example. In the second case, is it possible to have a graph with a bridge but no cut vertex? And I will say that the sort of silly answer is technically yes. If your graph is this very simple graph P2, or actually P2, it's a path with two vertices. Let's call them U and V. This graph has a bridge because if I deleted the one single edge, I'd be disconnected. I'd just have two single vertices. But it doesn't have a cut vertex because if you were to delete either one of these vertices, you'd be left with just one single vertex, and that graph would have one component. So it'd be sort of trivially connected. All right, so technically yes, but what about if we assume that it has more than two vertices? So assume the order is greater than or equal to 3. This is something that you're going to explore more in the exercises, but it's worth thinking about a little bit. Okay, now just like in section 2.1, when we said some graphs don't have any bridges, but maybe you can delete some subset of the edges in order to disconnect the graph, and we call that a cut set. We have an analogous definition for a subset of vertices that you could delete in order to separate the graph, and we call that a separating set. So a separating set of a graph is just some set of vertices such that if you deleted those vertices, the remaining graph is disconnected. So let's look at an example here. Let me label these A, B, C, D, and E. Now, if you delete any single vertex on the graph, it's still going to be connected. So there's no cut vertex on this graph. But maybe we could delete a couple of vertices and be left with a disconnected graph. And indeed you could, right? As one example, let W1 be, let's say, B and D. If we deleted vertex B and vertex D and every edge that's incident with those vertices, you'd be left with the following graph. A and E are connected, and then C is over here by itself. This is certainly disconnected. So this is an example of a separating set. So this is the graph G minus W1. Are there other separating sets? Probably. Here's a kind of silly one. If you were to delete B, C, and E, what would we be left with? Almost nothing, right? We've deleted all of the edges of the graph because every edge in this graph is incident with either B or C or E. And so we're really only left with A and C, but this is also technically, this is G minus W2. This is also technically disconnected. So this is another example of a separating set, right? But essentially what we want to get at is how can you minimally disconnect this graph? What's the fewest number of vertices that you could delete in order to disconnect this graph? We said it can't be one, you can't delete a single vertex, but we've shown that it's possible to delete two vertices and disconnect the graph. So we say that the connectivity of this graph is 2. We call in general, kappa of G, the connectivity of G, is the size of the smallest separating set of G. So kappa of G is going to be equal to 2 because we've found a separating set with 2 vertices, and we know that it's not possible to disconnect this graph using less than 2. Now there's sort of a confusing definition of what it means to be K-connected. All right, so just to be clear, this notation that we're using for connectivity is kappa, but we say that a graph is K-connected if kappa of G is greater than or equal to K. That is, if it requires a removal of K or more vertices to disconnect the graph. Okay, so what we can do is in the last example, we can say that G is 2 connected because it requires the removal of at least two vertices to disconnect the graph. But we can also technically say that G is also 1 connected because kappa of G is greater than or equal to 1, right? It's true that 2 is greater than or equal to 1. So we can say that G is 2 connected. We can also say it's 1 connected, and technically I guess you could say it's 0 connected. But you can't say it's 3 connected because it doesn't require at least 3 vertices to be removed to disconnect the graph. It's possible to do it in fewer. So this is sort of a tricky definition to get your mind around. But if it's K connected, then it's also M connected for every M that's less than K.